Hello, welcome to the review of Quiz 5. So this is, there we go. Let's give ourselves some more room. So yeah, this is the frequency response quiz and the second of our online quizzes. So let's go over the answers. So what we're looking at here is a generic system, a fairly generic system where the input is through a derivative on y, and then the output is through x, right? And we figured that out here in the directions. It specifies y is the input, x is the output, just in case you were curious, right? So this first question prompts us to find a generalized frequency response. So we don't assume that there is a derivative, or excuse me, a frequency that we're interested in. It's all frequencies, and we have a series of coefficients, and we have to construct in the quiz here, which is very tricky. So you have a lot of possible answers you could give, and you really need to know what you're doing. All right, so let's have a look at how to approach this. All right, so I'm gonna go ahead and copy this onto my paper. So the form of the equation was this. So to make things a little simpler, you'll notice that A1 is used in two places. That actually reduces the number of coefficients we need. That didn't have to be true, but it just happens to be true for this system. By the way, there are actually systems that tend to have these kinds of coincidental coefficients. Let's not get too sidetracked there. All right, so this is a frequency response problem, and because it's a frequency response problem, right away, without really even needing to think about it, we just know that we have to write this. Right? And we know that we need to write this. We've identified our input, y, so our input is always going to be this. We've identified our output, in this case it's x, so it's always going to be this. Right? And so now we just need to go about solving for z in terms of omega. So really the only thing we need to know now is how to take derivatives of e, which is, you know, like the easiest function in all of calculus to differentiate. So this is not so bad. J omega t. There you go. So x dot is equal to z j omega e to the j omega t, right? Just a quick review, and here's the tricky one, right? Negative z omega squared. Where did the j go? Well, you get a j omega squared, right? J squared is -1. Yeah, so in we plug. Great, we've remembered our derivatives. Now we just have to do, all we have to do is plug in and solve for z. All right, so normally to save time, right, this is where I ignore my e to the j omega t's. But just to be thorough and remind us all how this works, I'm gonna actually bother to write it out. So here we'll substitute this whole thing in, whoops, omega squared e to the j omega t. To save time, normally I don't bother writing that e to the j omega t because I know it's going to cancel out. It always does. If it doesn't, it means that we haven't done a very good job of choosing the form of our solution. If you remember, if you go way back to when we first studied this stuff, we went through a lot of effort talking about these exponential functions and why they're so good at solving this problem. And we did all that. We bothered to do that so we wouldn't have to think about it anymore. All right, so keep in mind there's no z on this side of the equation, right? The input does not carry a z. We're assuming that the input has a unity amplitude, right? This function is a sinusoid. It's a cosine. It's basically part of a cosine. And we've assumed a unity amplitude, so that whatever amplitude we get at the output, right, will be relative to this. If you double this amplitude, you double the output amplitude. Simple, right? So that way, the z here is in units of per amplitude input. Cool. All right, so as a result, there's no z here. There's only a z where you see the input terms. That's an easy way to accidentally goof up and lose points and not get a meaningful answer. All right, the next thing we can do for free is cancel out all of the e's because they appear on every single term. If I just rewrite what we've got here, it's going to end up looking like this. Let's start with my imaginary term. Why not? All right, A1 j omega. And then we end up with a naught here. And then minus A2 omega squared is equal to A1 j omega. So z is equal to A1 j omega divided by there we go. We have a numerator and we have a denominator, and then we've solved for z. In the denominators, we see has a real part, which is here, and it has an imaginary part. Now, this isn't part of the quiz, but you'll remember when we talked about this in class, because of this minus sign, it's possible for the real part to cancel itself out when you choose very special values of frequency. This term can go to 0. The presence of damping prevents the denominator from going to 0, but if you have very little damping or no damping, then things get very interesting. Z gets huge. So anyway, we've got our answer. Now let's go back to the quiz. How were we meant to answer it? Well, n1 is the numerator coefficient, and it was meant to be a1 j omega, right? So I need a j, a positive j, and I need an a1, right? So there's the way I would do that. Now that was the only term in the numerator. There is no other term, so this one is going to be positive 0, right? How did I know that? If you want to specify 0, make sure you specify positive 0. So then, yeah, there's that. So d2, the coefficient of omega squared, well, as you recall, that was negative a2. So I need a negative a2, right? Great. d1 omega, oh, that was j a1. Yeah, there was a j term, positive, and there was an a1 there. d naught, that was a constant term. That is counterintuitively negative. Or excuse me, a constant term, excuse me, that's positive. Silly me. Positive a naught. There we go. The omega squared term we already took care of. Okay. And then this is just a little hint as to how to do it. Obviously, this is not the answer. Okay. So that's how we do that. Next. Click. Okay. So here is a make-believe system. It is not the same system. It is slightly different. If you look, oh look, there's an a naught term in the numerator. So this is not the same system. So we want to take this system and we want to plug in a specific frequency. I structure the quiz this way in case you get the last question wrong, then you're not, starting completely with nothing. But it's clearly not a bizarre system. It's only a slight change from that actual system. All right, so let's switch over to paper mode. Click. And, all right, so Z is a1 j omega plus a naught. I'm going to plug in variables, or plug in values last, just because then I find that variables are much tidier to carry through algebra than numbers. It's much easier to see a mistake, or at least I think it is. Numbers just all look the same to me, whereas variables, I know where those variables came from. All right, so we want to, well, actually, I take it back. Actually, this is so simple that we probably should just plug in. So we want to calculate the response at a specific frequency. So we want to choose omega is equal to 1. We want to choose a naught is equal to 3.7, a1 is equal to 8.1. If these aren't your numbers, by the way, don't be shocked. I configure these quizzes to generate numbers on the fly, so you can so you don't all have the same numbers here. But these are the numbers the quiz gave me. So substitute your numbers and you'll get it. The point is that you understand the procedure, right? Okay, so A1 was, we said 8.1 times J omega. Omega is 1. It's J plus A naught was 3.7 divided by, well, here we're going to have the same term. That's just 8.1 again times 1 times J. That's from this term right here. All right, plus A naught, 3.7 minus A2 squared, 4.1, or times omega squared, which is just 1. There we go. All right, I can simplify that a little bit. Uh, 3.7 minus 4.1, let's see, that's what, just negative 0.4, right? Yeah, there we go. Negative 0.4. All right, I'm not done. I need to reduce this to magnitude and phase. So it's a complex number, right? So remember, the length of the complex number vector is our magnitude, and the angle relative to the real axis gives us our phase, right? So that tells us how the output is phased relative to the input. So to do that, we swap over into polar notation. All right, so here this is equal to, let me bring up my handy dandy calculator. By calculator, I mean my Python terminal. Okay, so this is going to be, let me actually write out what I'm doing. So there's that. So that's the magnitude of the numerator with an angle that is the arctangent of the imaginary over the real. So that's going to be 8.1 divided by 3.7. Okay, and all that is divided by 8.1 squared plus negative 0.4 squared All right, now remember, when you have a negative sign in the arctangent, that is a red flag that you need to look out to make sure that you're in the correct quadrant. Let's do a quick sketch and make sure we're in the correct quadrant. Here's my real axis, here's my imaginary axis. I have an 8.1 in the J, that's positive, so that's up here. And my real is negative, so I'm down here. So the angle I'm going to get needs to be in this quadrant. So if we get an angle in this quadrant, no problem, you just add 180 or subtract 180, either way is fine, and you get the correct, and get it in the correct quadrant. Did I say 180? I meant pi, right? Because radians, you know. Yeah, you can do either one. Doesn't matter. Okay, so let's start calculating, shall we? 8.1 squared plus 3.7 squared. Square root of that is, so that's 79.3. Square root of that is 8.9. So it's just a little bigger than this guy. That makes sense. 8.9. I'm going to go ahead and carry out some extra sig figs just because. 8.905. There we go. With an angle of, I'm going to work in radians because that's what Python's going to give me natively. that's 1.1423. Again, just crazy number of sig figs, right? I'll round at the end. All right. In the denominator, it's awfully similar in magnitude, except that the real part is tiny. Because why is that? Because we were close to resonance. We were very close to resonance. But we see the damping term is actually dominating in both of these. The damping term is way bigger than the real term in both of these. So the answer is not actually that horribly different. It turns out to be 8.1 099. Crazy number of sig figs. No way am I going to know this that precisely, but it makes sense for now. All right, so I'm using a function called atan2, which automatically handles the quadrant nonsense, so I don't really need to think about it. The answer ends up being 1.6201. That's as far as I'm going to go. That's already an insane number of sig figs. So my final answer then is 8.905 divided by 8.905 divided by 8.1099. All right, so the magnitude turns out to be 1.098, so about 1.1. That's close enough. With an angle of, now we just need to take this and subtract this. Right? So that's 1.1423 minus 1.6201. And the answer is negative. So the input is going to lag by about 0.4778. That's radians. Let me just be really clear that I'm working in radians. Or it's about 30 degrees. It's a little less than 30 degrees. Yeah, there we go. So we have a slight amplification, just 10%. A 10% amplification, not a whole lot, and we're lagging by about 30 degrees. Okay, so if I can just pop back to the quiz for a moment. Yeah, so all I asked you for was the magnitude. Wasn't that kind of me? Yeah, so I would just enter 1.098, and then I'm done. Okay, well, thanks for watching. I hope this was helpful.